Okay, so in this video, we're going to continue our discussion of orbitals, exactly how electrons go into them in the end, kind of what this affects, and how we can identify core and valence electrons and all of this good stuff. So, why does all this information about orbitals matter anyways? So I was being a bit vague about orbitals last time. We were trying to just nail down these models and understand what the heck I was talking about, that electrons aren't exactly real anyways. I just want to remind you again that electrons are both a particle and a wave of probabilities where that particle exists. So they exist as this wave of all the options of locations of where they could be until they are observed and forced to choose one exact location. And remember that orbitals tell us about these probable locations of the electrons in the electron cloud. So we never know the exact locations of electrons around an atom. So we use orbitals to tell us how likely it might be to run across a certain electron in a certain space, kind of deal. Different orbitals have different energies of sort of generally increasing from the center of the atom outwards. And when they jump orbitals, electrons do. That's what causes our emission spectrum still. And we can use the probabilities given by these orbitals to fill in the most likely locations of our electrons around an atom. So based upon the locations of these electrons and how easily atoms can therefore form bonds and how many bonds they can form, of course, affects the chemistry that everything is involved in. Okay, so we're talking about orbitals. We gotta start talking about how to name the orbitals, how to talk about them. Been kind of vague about it. It's time. So orbitals are denoted by both a number and a letter, okay? So one tells us more about the energy and one tells us a lot about the shape. So when we're talking about the number, this is called a principal quantum number. So this denotes the general energy level of the orbital. So we usually see this denoted as n equals 1, n equals 2, n equals 3, and n equals 4. So the energy levels are basically kind of like fixed distances from the nucleus. So rather than being, again, that individual ring, this is representing kind of a spatial distance, 3D space around the nucleus. But it's not like exactly saying like there's a ring, because there's all these other informations about the shapes of the orbitals and the likelihood of electrons to lie in those as well. However, generally, as you increase distance from the nucleus, you're increasing the energy level, so the principal quantum number increases to represent that. So an n equals 1 energy level is going to be lower than an n equals 2, is going to be lower than an n equals 3, and n equals 4. And as we start to get up in energy levels, they become closer and closer together. And because they become closer and closer together, we'll see that this has some funky effects on the way we fill our orbitals, but that's just a huge preview. So again, the principal quantum number denotes the general energy level of the orbital, kind of the general how far it is from the nucleus, and things that have high energies, have high principal quantum numbers, and are further from the nucleus. So you can have multiple orbitals of different shapes, like that S shape we saw last time, the P shape, and that D shape. So we could have orbitals of different shapes all have the same principal quantum number. And so we would call this a principal shell. So a principal shell is all the orbitals with the same principal quantum number. The book uses this term more than I will. You probably won't hear it out of me again unless I'm trying to explain something and I have no other word. But again, this is all of the shapes, all of the letters that have the same number are a principal quantum shell. Or principal shell. Sorry. Okay, so we talked about the numbers. Well, what about the letters? Well, as in like the first half of the first video, we know that we can use letters to denote the shape of the orbital. So I'm in the way here, but remember the s orbital is that circular sphere shape. The p orbitals are made up of 3 dumbbell shapes, and the d orbitals are made up of 4 four-leaf clovers and a donut with a dumbbell. Kind of a deal. So this is an s orbital, a p orbital, and a d orbital on your screen. So We use these, or we have these different shapes, and we can kind of call these subshells. So if the principal quantum number, all the same principal quantum number is a principal shell, these are the subshells. Again, you probably won't hear me use this term quite so much, but the book uses it, so it's out there. So the shapes also have a generally increasing order of energy, right? So things that are close to the nucleus are low in energy, and things that are further from the nucleus are higher in energy in general. We talked about that, right? So when we're looking at an s orbital, it's this sphere around the nucleus. So really, it's close in by the nucleus. They tend to be lower in energy levels. P's tend to be higher in energy levels. We can see that the electron density, where it's the highest concentration of where an electron might be, is a little bit further away from that nucleus. And they're in these three different positions kind of all the way around, excluding that center. So that's a little bit higher in energy. They tend to just be a little bit further away than the electrons in an s orbital. And then in d orbitals, you see it spreads them even further out. It's less likely that these are going to be, or that the electron's going to be very close to the center of that atom. So as you increase from S to P to D, you generally increase in energy, just like when you increase the principal quantum number. However, the principal quantum number tells you more information about the energy than this does. And the thing is that these, we're not like kind of nailing down a specific amount of energy, but because they also increase in energy, and because we have principal quantum numbers increasing in energy as well, we'll see that there's a little bit of a funky thing that happens in just a second here. So just keep in mind that these increase in energy as well. So again, just to give it a little bit more of an analogy, I'm going to use 2 or 3 today. So this is just the first for just this scenario that I want to discuss. It's almost like the principal quantum number is sort of like the country. So I could tell you I'm in the United States, but I could be in all 50 of the states, any of the outlying territories, whatever you want to call them. So I'm in the United States. It doesn't really tell you a whole lot, but it at least tells you what country I'm in. The letter is like the state of the union the electron lives in. So it's a more specific piece of location information kind of hidden in there. So if I tell you I'm in Illinois, you have a higher chance of finding me than if I tell you I'm in the United States. So that's kind of the idea here. It's like we've got a state, and then that energy level, that n equals 1, n equals 2, n equals 3, n equals 4, so on and so forth, that's going to be more like a general piece of information. And again, as I mentioned before, these orbital shapes kind of come in groups. So S is only made up of 1 orbital, but P is always made up of 3 orbitals, and D is always made up of 5 orbitals. So these are almost like kind of the towns in the state. We can narrow down our state into just a little bit more piece of specific information even. It's not just a broad idea. So again, anytime we see a p orbital, we're talking about 3 different sets, or like one set of 3 different options for locations. And when we're talking about a d orbital, we're talking about 5 different options, all combined to one to make one d orbital. So here it is, the slight catch I mentioned before. So again, while orbital energies kind of, you got the principal quantum number increasing in energy, and while the orbital energies generally increase as you go up in shape from S to P to D to F to G to H. I didn't mention those, but they technically exist. We won't talk about them in this class. But in reality, it doesn't just exactly work where you go 1s, 2s, 2p, 3s, 3p, 4s, so on and so forth. It gets a little weird. So actually, when things increase in energy, we go from 1s up to 2s, up to 2p, up to 3s, up to 3p, up to 4s. Makes sense so far. But wait, what's this guy over here? 3D's kind of out of order. Basically, because the D shape is such a high energy, 3D ends up being a higher energy than 4S is. So it's higher in energy. It kind of breaks some of the ideas we have about distance and these shapes and stuff like that. But when we actually look at it in real life, this is how everything is affected. So it kind of takes things out of order just a tiny bit. Okay, so now we know all about orbitals. We've talked about what they are, the nature of all of this. Now how do we actually put the electrons in them? They're probability maps. How do I figure this out? So here's my second analogy. So the first one kind of talks about the difference between principal quantum numbers and the letters representing the shapes, those subshells. Now we're going to talk about orbitals as locations for electrons, okay? So let's think about orbitals now as all the rooms in a hotel. The hotel is the electron cloud of the atom, and the orbitals are like all the hotels in a hotel room, and electrons are like the people going into rooms. Let's say it's a honeymooners weekend, right? So we've got pairs of people that need to go into rooms potentially, and they might be arriving at different times, let's think. So when you're booking a hotel, you don't just put any kind of person in any room, right? You know, everybody wants to stay with their spouse and to have the people around them that they love, right? They don't want to stay with some random person they've never met before. You don't just throw random people into random rooms at random times. There's order to how you put people in hotel rooms. And you do not cram all 100 guests you have staying in the hotel at night into one 2-bed room. You don't do it. You have to spread them out throughout the rooms in the way that makes sense, that gives them the best option for what they need. So let's do it. Let's put our electrons in their rooms, tuck them into bed, and say goodnight. So orbitals are like the likely space for a certain number of electrons to exist. So we're going to use some guidelines to place our electrons in there. So how do we do this? We actually call a visual display of the location of the electrons in their orbitals an orbital diagram. So when I'm looking at the things that are pictured on your screen here, all these weird looking boxes, these are what we call orbital diagrams. So each arrow represents an electron. So lithium has 3 electrons. So this is 1 electron, 2 electrons, 3 electrons. Kind of see they got that weird half-looking arrow? So they have that weird half-looking arrow. It's showing us something we don't know quite what it is yet. So there are these weird half-looking arrows. And each box is an orbital. Okay, putting electrons in orbitals, I'm going to put electrons in a box. So remembering that S is always just 1 orbital, but P is made up of 3. So I'm going to use 3 boxes for P, and I'll use 5 boxes for D, because again, a P is always made up of 3, a D is always made up of 5, but S is always just 1 box. We tend to write the number and letter of the orbital down below. So the number and the letter, so this would be the name of the orbital. I said write letter and name, but letter and number, that is the name of the orbital. So 1s, 2s, 2p. And we group the orbitals together with the same number and same letter. So we're scooching all the p's together, the 2p group. We're scooching them together as a group is what I'm saying. We're not going to like space out all of the 2p orbitals from each other. Each orbital holds 2 electrons at maximum. We consider one to be spin up and one to be spin down. So that's what that half arrow means. This one's pointing up and this one's pointing down. It's a half arrow because now it's a part of a pair. So spin up and spin down is kind of a weird concept. As we move into this quantum mechanical model, things kind of become very abstract. So spin up and spin down has nothing to do with spinning. It is just a word we use to describe a characteristic that basically says these two electrons have decided to be a pair together and they're willing to hang out with each other as long as one takes one version of the characteristic and the other takes the other version of the characteristic. So we call that characteristic spin, and we say that one electron is spin up and one electron is spin down in a pair. Okay? It has nothing to do with up and down. It has nothing to do with spinning anything. It's just like we decided one day that this hand was left and this hand was right. There's no reason for us to have chosen one word over the other to have meant one. We chose arbitrary words to describe something so we could talk about the difference between two things. That's what we've done here. We have chosen spin up and spin down. And now this is why electrons are able to form those pairs that we saw in our Lewis diagrams, is because even though they repel each other, they kind of make this agreement, all right, you're spin up, I'm spin down, so we can hang out. I'm cool. As long as you're spin up and you stay in your lane and I'm spin down and I stay in my lane, we can hang. Otherwise, no go. Not happening. No. So, each orbital holds two electrons at maximum, one spin up, one spin down. We fill orbitals from the lowest energy to the highest energy. So in this case, we see here we have 1s, goes to 2s, goes to 2p. Makes sense. 1 is the lowest principal quantum number. 1s would be lower than 2s, and s is a lower energy than p. Makes sense. So we're filling our orbitals this way. We can see as we increase our number of electrons, we're filling our orbitals from 1s up to filling up the 2p orbital. And when we do this, we put one electron per orbital until we're forced to pair them up. Kind of like those Lewis structures when we were drawing them. That's again what's happening here, is it's because these electrons stay apart from each other in their orbital, they don't pair up until they're forced to. So that's what we were seeing happening without knowing it in the background. So it's kind of explaining some of the stuff we saw last chapter. Kind of cool. And so I just want to remind you very quickly here where these electron numbers come from. How do I know how many electrons something has? Well, remember, in a neutral atom that doesn't have a charge, the total number of electrons is equal to the total number of protons, and the total number of protons is given to us as the atomic number. So that atomic number is given to us, and that's also in our case here going to be our number of electrons, because it's the same as the number of protons that the atomic number represents. So, remember, as I said before, that we kind of have that weirdness in the energy levels, and we have to make sure we fill everything from the lowest energy level up to the highest energy level, okay? So we're filling from the lowest energy level up to the highest energy level. And we know that there's kind of these weird tricks where 4s is technically lower in energy than 3d is. So how can I remember this? How can I figure this out? How can I remember how electrons fill orbitals? Well, here's our periodic table. Now's coming in our periodic table explanation. So when we're filling these orbitals, we're filling them from 1s to 2s to 2p to 3s to 3p to 4s, all the way back to 3d to 4p to 5s to 4d to 5p to 6s, so on and so forth. That's kind of a funny, weird looking diagram though. How can I remember this? Again, our periodic table's back. It has all the information you could ever need. I do have one that has all the information you could ever need. However, this one's giving us a little bit more of a highlight about our orbitals and how our electrons fill our orbitals. So let me show you this. Anything in blue is considered a part of an s orbital. Anything in pink is considered a part of a p orbital. Anything in orange in the center here, the transition metals, that's the d orbitals. And down here at the bottom in green, we're not going to talk much about this, but these are the f orbitals. Again, we're not going to talk much about them in this class. This is the only time you're going to hear it. And so we might talk about this as the s block. So these are s block elements where their outermost electrons are in the s block. We'll talk about what that means later. In the p block, again, the p block is all of these elements that have electrons in the outer p, or that all of the outer electrons lie in the p orbital. Again, the d block here representing the same thing, and the f block down here representing the lanthanides and the actinides. So you might hear me say, oh, that's an s block element, that's a p block element, so on and so forth. And so, let me say this. Hydrogen and helium, their 2 electrons represent the 1s orbital. Lithium and beryllium, theirs are the 2s. These are the 2p. This is the 3s. This is the 3p. Okay? Row number 1 has the 1s. It only has s elements. Row number 2 has the p block too. So it has these 2p and the 2s and the 2p over here. So this is the 2s. I misspoke there. The 2s and the 2p. So when I look at the periodic table, I'm always in my head going 1s, 2s, 2p, 3s, 3p. Okay? So that row, for the most part, corresponds to the N number, that energy level number. So that energy level number is most of the time what you see here on the left-hand side of the periodic table. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. All right, it's weird. It feels wrong. Icky. Okay, so when we get to the D block, the first row in the D block is the 3D. So we go 1, 2, 3, 4, 5, 6, 7. That works perfectly fine for the S and the P. But when we get to the D, it actually starts at 3, not at 4. So this is the 3D block, okay? So that's kind of how you can remember how to fill your orbitals on the periodic table. My lowest in energy is 1s, then I would go 2s, then I would go 2p, then I would go 3s, then I would go 3p, then I would go 4s, then I would go 3d, then I would go 4p, then I would go 5s, then I would go 4d, then I would go 5p, okay? So at the very most, I will give you xenon. In this class, we're not going to go beyond xenon.